Okay, my name is Chuck Lynch, and in this talk, I'm going to be telling you about some of the work we're doing in Connor Liston's lab in the Department of Psychiatry at Weill Cornell related to personalized TMS targeting of functional networks mapped using resting state fMRI data at the level of individual patients. And I'm going to start by talking about this approach called precision functional mapping and why I think it has a lot of potential in the context of personalized TMS targeting. Precision functional mapping, or PFM, is simply the practice of delineating functional networks in areas at the level of individual subjects, usually using resting state fMRI. And this approach stands in contrast to how functional networks are usually studied, right? Which is, generally speaking, acquiring small quantities of resting state fMRI data from many, many individuals, sometimes hundreds or thousands of people, and aligning all that data in a common atlas space and averaging it and mapping our networks in that group average data set. When you take this approach, you usually end up with a map that resembles what you see here in A, which is essentially a description at the population level, central tendency for how functional networks, like the default mode network, which you see in red here, or the frontoparietal network in yellow, a central tendency map for where these networks tend to be located approximately. What PFM has shown us over the past few years, however, is that at the individual subject level, when we map these networks, there's marked variability in terms of how these networks are organized, their size, their shape, their spatial arrangement, to the point where this group average map only gives us a rough idea of how networks are organized in any particular individual's brain. The analogy that I like to use to drive home this point, as well as think about why this could be really important to consider in the context of TMS targeting, is to think about what would happen if you took pictures of individual human faces, aligned them, and averaged them. What you would end up with is what you see in the middle of the slide, which is a kind of group average human face. It does have a lot of the features that you would expect to find, like eyes, a nose, and a mouth. But if you think about all of the individual faces that went into making this average description, this average map doesn't really describe any single one of those people in any accurate way. And at least at a conceptual level, you can think about what we're doing with our resting state functional networks as being kind of the same. We are taking data that has a lot of idiosyncrasies, a lot of individual differences, and generating a group average map, which gives us a sense of the central tendencies of how these networks are organized. It doesn't really describe any single patient accurately and may not be that useful for something that could require a lot of precision, like TMS targeting. So if you think about, for example, one of the most common anatomical targets, especially in the context of treating things like major depression, one of the most common targets is dorsolateral prefrontal cortex. And as you can see at the top of the slide, this is a region where there's enormous variability person to person with respect to how these functional networks are arranged spatially. So on the left, you see our group average description, and on the insets to the right, you see 8 patients with depression and the kind of arrangement of these functional networks in this cortical area. And as you can tell, the same networks are represented in each patient. They're just, there's a lot of variability in terms of where they're located. And this observation kind of leads naturally to the expectation that a generic one-size-fits-all strategy for TMS targeting, where you're placing the coil over the same part of DLPFC, we could inadvertently be stimulating different functional networks in different patients. And why this matters, one of the leading hypotheses for why there's variability in treatment response to our TMS is that the functional properties of the stimulated tissue could be one explanatory factor amongst many. So all this information sets the stage nicely for the talk I'm going to be giving here, and that's that individual brains exhibit a very idiosyncratic functional organization that can be reliably mapped using resting state fMRI. However, spatial targeting for TMS protocols is generally not individualized. So in the study I'm about to talk to you about, we took one of our data sets of highly sampled patients with mood disorders. These are 8 individuals that we've studied longitudinally for over a year in some cases. So we have tens and tens of hours of data on them. And we generated these really precise maps of how functional networks are organized in their brain. And we asked the extent to which individual differences in that organization could impact the ability of TMS when applied in this kind of generic one-size-fits-all manner, limit its ability to selectively engage any particular brain network. We then go on to develop and validate ultimately a new method for what we hope will be more precise individualized targeting. And this is an approach we call targeted functional network stimulation, or TANS. So what I'm showing you here is the first analysis we performed, which is an electric field modeling experiment relying on the SimNibs software package. What you're seeing in A are functional networks mapped in each patient's brain. B, the electric field that was generated when placing the TMS coil in the simulation over the exact same part of DLPFC. So we take the set of MNI coordinates and back transform them into each patient's brain, identical coil handle orientations. And C, we're just operationalizing what we're considering to be, for convenience, the hotspot, so the strongest portion of the E field, and we identify that using a percentile-based threshold. We can then ask within that hotspot which functional networks would likely be engaged in each patient. So in the inset in C, you can see the different colors representing different networks that would be stimulated. And in D, these are kind of stacked horizontal bar plots where each row is a different patient, and the size of the segment of the bar plot, the color represents for a particular functional network how much of the E field was on it. And the key finding here is that different functional networks tended to be stimulated across individuals. So for example, in MDO6 and MDO3, the frontoparietal network was primarily stimulated, whereas in MDO1 and MDO4, the salience network received far more stimulation than the frontoparietal network. The other kind of interesting finding here that we weren't necessarily expecting was that there are often multiple functionally discrete networks that are simultaneously stimulated within any given individual. So the default mode network and cognitive control networks like the frontoparietal dorsal attention network, for example, are thought to be very similar things. And in nearly all of these instances, we're seeing evidence of those two kinds of networks being simultaneously stimulated, which may or may not be desirable in the context of a treatment. So these findings motivated us to try to develop a new targeting approach that leverages PFM to generate precise maps of each individual's unique functional network architecture, as well as their unique cortical folding patterns, in order to find a coil placement that will be useful for engaging a target network while also minimizing stimulation of non-target networks. This approach ultimately incorporates elements that are present in many other E-field-based targeting approaches that exist currently, such as the use of the SimNibs E-field modeling software, as well as this kind of brute force grid search procedure where we're kind of iteratively testing out many different coil placements. But TANS differs from existing methods importantly in two ways. One is TANS is seeking to align the overall spatial distribution of the E field, and especially where it's strongest, which we kind of refer to again as the hotspot for convenience, with the target network's overall functional topology. Whereas existing methods take a single spherical ROI in the volume and place that somewhere within, in the case of targeting a functional network, you would place it somewhere in the target network. And the method would try to maximize the E field strength at that fixed point. But it doesn't, generally speaking, consider the strength outside of that single ROI. And to give you a little preview of one of the findings I'm going to be sharing with you later on in this talk, that this approach becomes very vulnerable to high levels of off-target stimulation. TANS avoids this by specifically penalizing for off-target stimulation and even giving the user the ability to specify regions of no interest. Without getting too much into the nuts and bolts of how the approach works, I just want to describe at a conceptual level like the main steps. The first part is deciding which part of the network should be targeted in order to maximize stimulation specificity. Functional networks have representation in multiple cortical zones and usually have bilateral representation. So if we want to selectively stimulate a network, the first thing we have to decide is which part of the network we should be stimulating. And the approach that we take is identifying the largest piece of the network that is going to be accessible to TMS by virtue of being located on a gyral crown instead of buried in a sulcus or on the medial wall, for example. Once we've identified that target network patch, we identify the nearest point on the scalp. And that point on the scalp closest to the center of mass of the target network patch will become the center of a a circular search grid on the scalp, where we're going to have many different points in the scalp where we're going to be testing coil placements and orientations. The user can set the search grid to be as small or as large as they want. We find 20 millimeters works pretty good. And the search grid itself can be subsampled, again, to reduce the number of simulations that need to be performed while not sacrificing accuracy too much in most cases. After we've run all of the simulations, which takes some time, you then kind of iteratively loop through all of those possible coil placements and ask the extent to which the E field that that coil placement produced produced something that was on target or not. And what I'm showing you here on the top row is an example of a coil placement that was not ideal by virtue of stimulating, this non-target network. So in this example, we're targeting the frontoparietal network, and you can see on the top row, the salience network, this black network, receives more of the stimulation than the frontoparietal network in yellow. The placement that's ultimately identified as being best is one where much more of the field is being delivered to this target network. Once you have the optimal coil placement, you can consider things like the optimal dose. So you, with a fixed coil placement, rerun a series of simulations where you're iteratively increasing the stimulation intensity. And given an assumed, if you have some kind of a priori information about what the neural activation threshold should be in this patient, you can ask how much of the super threshold portion of the field is on target. And it's essentially what I'm showing here is left to right, we're increasing the stimulation intensity, and you can see at lower stimulation intensities, there's no tissue that's being stimulated. As you increase, you kind of initially have very, very high stimulation specificity. This little tiny patch of frontoparietal cortex, the target network is being stimulated, but you're only stimulating a very small portion of the network, right? So it's desirable probably to hit more of the network. So you increase the stimulation intensity. But as you do, you start to sacrifice specificity, right? You start to hit non-target networks. And this relationship, this trade-off between intensity and stimulation specificity and the amount of tissue that's being stimulated is captured in plots like this. So, it's probably ideal to try to find some compromise between the two. So kind of going back to the analysis we performed in our paper, the first thing we asked was whether or not TANs could be used to find a coil placement for targeting the frontoparietal network in each patient. What I'm showing you here is an A, the coil placement that was identified by TANs, B is the electric field associated with that coil placement, and C is similar to what I was showing you before, the kind of operationalized hotspot, as well as the networks that fell within that hotspot. And you can see it's immediately clear relative to what I was showing you before, much more of the yellow frontoparietal target network is being stimulated in each of these patients, as was the goal. On average, about 71% of the hotspot was on the target network. So this is an improvement over what I was showing you previously. But to kind of further contextualize this performance, we reran the analysis using an alternative targeting approach called the auxiliary dipole method, or ADM. ADM is designed to really quickly find a coil placement that maximizes the strength of the electric field in a specific sphere defined in the volume. And as I was kind of describing before, this approach, like others, isn't well suited for the problem, may not be well suited for the problem of stimulating functional networks, because functional networks, especially when defined at the individual subject level, exhibit a very complex shape topology. And often you have functionally discrete networks that are interdigitated with one another. And this kind of sphere ROI isn't going to really describe that topology very well. So it's vulnerable to kind of increased levels of off-target stimulation. And this is exactly what we found. So what I'm showing you here is the initial kind of distribution of networks that were stimulated when you're just placing the TMS coil over the same part of the LPFC. B is using ADM, where the ROI for ADM is set in the center of the target network. You can see we're hitting the frontoparietal network in those cases, but we're also hitting many other networks at the same time. Whereas with TANs, we're having increased stimulation specificity. So although there is still some off-target effects, it's relatively speaking, less than with the other two approaches. And that's captured here, where you kind of see this stepwise improvement going from the generic approach in the circle, square, ADM, and the triangle being TANS. And the y-axis is the stimulation specificity, and these are just different individual subjects shown here. And just next, we kind of digged into a little bit more what's going on with ADM, and what it boiled down to was that, as you know, ADM is designed to operate this way. It's designed to maximize stimulation intensity at a fixed point, but it doesn't consider the stimulation, maximize the E field strength at a fixed point, but it doesn't consider the strength of the field outside of that fixed ROI. So although it did exactly what it was designed to do, it maximized the E field intensity at one point in the network. It came at the cost of lower stimulation specificity overall, because that coil orientation and placement that increased the stimulation intensity at that one point necessitated some off-target effects. And in fact, in 5 of the 8 patients we tested, there were non-target networks that received a greater level of stimulation than the target network. So this kind of highlights the issue I was referring to before about the non-target stimulation. So finally, all of what I've shown you so far are just simulations performed retrospectively in an existing data set that we had. So we wanted to test prospectively whether or not TANS could be used to improve stimulation specificity. And we did this by targeting different somatomotor networks and primary motor cortex in a handful of healthy individuals. So different networks can be identified using resting state fMRI in somatomotor cortex, and I'm showing you examples of those here in A, where green, cyan, and orange correspond to the foot, the lower limbs, the upper limbs, and the mouth, the face, respectively. And what we did was we applied both ADM and TANS to identify coil placements for targeting each of these, or 2 of these networks, the foot and hand. And what you're seeing here in B are the E fields associated with those coil placements that were identified. So the left column is ADM, the right column is TANS, top row is somatomotor foot, and the bottom row is somatomotor hand. And what you can see is something already that was very consistent with the simulations we had performed previously. There's an instance here where when ADM is targeting somatomotor foot, you can already tell that there's going to be a high amount of stimulation that's also delivered simultaneously to somatomotor hand, this little hand knob right here. Whereas with TANS, because the non-target network is explicitly set as an avoidance region, we're able to generate electric fields and coil placements that will kind of selectively engage these 2 targets. In short, what this experiment involved was using motor evoked potentials as our kind of readout of both on-target and off-target effects by virtue of having movements in a target versus non-target limb, respectively. And we did this by just simply monitoring visually for movement in those limbs, so the experimenter would watch. But we also had a 2-channel EMG hooked up to the hand and the leg to monitor for movement. And we administered single pulses with intensity ranging from 30 to 80% of maximum stimulator output, delivered using MagVenture's B70 coil. And in all 3 subjects that we tested, so the first subject was on the previous slide, these are the kind of 2 replication subjects. In all 3 subjects, we found that TANS was able to produce movement in the target limb, and at no intensity did we observe movement in a non-target limb when using TANS. In contrast, in 2 of the 3 subjects, as kind of the E-field modeling suggested would be the case, we found that ADM produced motor evoked potential in a non-target limb, specifically in the hand when targeting the foot, in 2 of the 3 subjects. So this kind of speaks to the issue of stimulation specificity, and in this case, TANS performed as expected. It was able to engage these 2 targets selectively. So to summarize, TANS, our kind of individualized targeting approach, referred to as TANS, achieve significantly more selective stimulation of the frontoparietal network, which was specified as the target in this case, in 8 highly sampled patients with mood disorders. We then designed an experiment in a handful of healthy individuals where we asked whether or not TANs would be able to selectively engage different somatomotor networks. In this case, they corresponded to the upper and lower limbs. And as expected, we found TANs was able to do so, and alternative approaches that don't penalize for off-target effects in some cases led to inadvertent stimulation of non-target representations. And collectively, we think these findings support the feasibility of precisely delineating and selectively targeting functional networks at the level of individual patients. There remains an open question whether or not selective stimulation is something that will be something that's important in the context of brain stimulation interventions. It could be the case that it doesn't matter, but having tools like TANs where selective stimulation is possible, we think is going to be kind of necessary tool for testing these hypotheses in the future, which is something we're planning on doing. If you're interested in this data and the method, I encourage you to check out our recent paper published in Neuron a few months back. And recently we have a protocol paper which came out in Star Protocols, where we kind of walk through step by step how to use TANs, and we have links to an example precision functional mapping data set, which will allow you to, you can download and test out the method for yourself. So with that, I want to thank all of my co-authors, especially my PI, Connor Liston, Emmanuel Elbow, and Jonathan Power, who were my kind of volunteers for the motor evoked potential experiment I described, and a whole bunch of other folks who helped collect data and process it and helped enormously. So thank you. And if you have any questions, please feel free to reach out to me. And thank you for your time.